In this video, we're going to look at experiment 4, which focuses on chemical reactions. There are two parts of experiment 4. One we're going to do, and the other one we're going to wait and kind of do that in experiment 5. So the first part of experiment 4 focuses on redox reactions, and that's what we're going to be doing today, is looking at a whole variety of redox reactions. And then in experiment 5, we're going to take a look at metathesis reactions, and we're going to focus in on metathesis reactions for experiment 5. So the latter part of this, part C, we're not actually going to be doing today. We're going to be looking at all of the metathesis reaction stuff when we do experiment 5. So this experiment is going to focus on chemical reactions and particularly on redox reactions. So a couple of concept questions I want to look at in just a few seconds. But first, I kind of want to walk you through one type of redox reaction that we're actually not going to do today, but I want to demonstrate it for this. So we wouldn't actually even do any of this type of reaction, even if you were in class physically. It's not a reaction that we do, because these tend to involve explosions. So let me show you what one type of redox reaction looks like. And I'm going to use this video from the Mythbusters and show you some of their best explosions, which is a type of redox reaction.
So sit back, relax, and enjoy the chart-topping, most memorable Mythbusters greatest hits.
Okay, so let's talk a little bit first about what we just saw. So the last few experiments 2, 3, and 4, have been dealing with processes, basically, whether they're physical or chemical in nature. So in experiment 2, we looked at physical processes, where we saw that the material changes its form, but not its chemical contents. And then in experiment 3, we started to look at how things react chemically, where they actually change their chemical makeup from the reactants to the products. So now in experiments 4, 5, and 6, we're going to look at those chemical reactions, but we're going to start to break them down into different types. So in experiment 4, we're going to focus on redox reactions in particular. And the redox reaction that I showed you in the video, that class of redox reactions is called combustion reactions. And that's basically where you take some kind of hydrocarbon or carbon material. It could be an explosive, it could be like wood in a fire, it could be some kind of material that contains carbon, or basically any element, and you react that material, whether it's made of carbon or some other elements, with oxygen, and then you produce carbon dioxide and water. So that's the typical combustion reaction, is you take something like, it could be ethanol, methanol, wood, you react it with oxygen, and you make carbon dioxide and water. And what you're doing is you're using oxygen as an oxidizing agent, we're going to talk a little bit more about that, to steal electrons from that hydrocarbon. So you're transferring electrons, and in doing so, you generate heat and flame. So now we kind of know what a chemical reaction is, and we're starting to get a sense for how do we know chemical reactions have taken place. So some of the things we look for are things like color changes, things like heat being released or a gas being released. It could involve, like I said, heat transfer, and it could also involve the production of light. That could be an indication that something is giving off heat. But there's a whole slew of observations that we can make that tell us that a reaction takes place. And then what types of chemical reactions are there? Well, in Gen Chem, we're going to focus on two main categories. The first is redox, and the second is metathesis. And metathesis is a very large blanket that includes acid-base, precipitation reactions, and gas-forming reactions. Okay, so we're going to look at another chemical reaction, which is similar to a combustion reaction, and it almost is a combustion reaction in a sense, because in this case we're reacting oxygen not with a carbon but with iron. So this video depicts what happens when you burn steel wool. Now, steel wool is basically just a piece of steel which is made primarily of iron, but it's in this form where it looks kind of like this. So let me just show you the video. So steel wool is this mesh-like form of steel where it's basically in these little teeny tiny wires, and when you add a flame to give it a little bit of heat, you can see that the wool begins to burn, in essence, or combust, and it forms a compound called iron oxide. So we're going to use this as an example redox reaction. This is not one that we would actually do in class, but again, I show the video because it's very interesting. And you can see that because the steel wool has a very large surface area, it's able to react very, very quickly and give this very dramatic sort of thing. Now, one thing you'll notice too, and this is kind of important, you'll see here that when they try to burn the steel wool and it's still very compact and not opened up, it burns very slowly, and that's because this reaction needs oxygen. So by opening the steel wool and exposing it, you'll make it burn much quicker. So if you compare the burning of it all together versus when it's spread apart, you can see that it burns relatively fast when it's all opened up, and then when it's closed, it burns slower because the oxygen can't get in as fast. So now let's look at some concept questions that we need to start to discuss when we talk about redox reactions. So we have to talk about what is an oxidation and what is a reduction. We're going to break this down in a few more seconds on the next slide. We're going to break this down in more detail, but for now, let's talk about, generally speaking, what these things are. So when something is oxidized, that means that compound has lost electrons. So the compound that starts as a reactant and goes to a product, the compound that has an oxidation number that increases, meaning it becomes more positive or loses electron, is oxidized. And the compound that's reduced, or its oxidation number goes down, meaning it's gained electrons, is the compound that's reduced. So that when you have a reduction, that means you've gained electrons. When you have an oxidation, that means you've lost electrons. So now, oxidizing and reducing agents are basically, it's a statement that says that this particular reactant either causes oxidation or causes reduction in the other reactant. So the compound that is oxidized, meaning that it has been oxidized, is therefore the reducing agent. It has caused the other thing to be reduced. Whereas the thing that's been reduced, the reactant that's been reduced, has caused the other thing to be oxidized. So that is the oxidizing agent. So we're going to start to dissect this in a few seconds for this reaction of iron oxide. And then how can we tell if this reaction is exothermic or endothermic? Now, in your observations of this, one of the things that you're going to be doing today is making some detailed observations. I want you to think to yourself, what observations can you use from this video that, without even standing there and putting your hand next to it, is that this reaction is either exothermic or endothermic? So take a second and think about that. Now, hopefully, one of the things that you might have thought about is the fact that this gives off light. When something gives off light, that tends to be associated with something that's also giving off heat. Because when you heat something up, like, for example, an element on a electric stove, when you heat that up, that heat is associated with it giving off light. And that's because when you have a lot of heat around, you can excite electrons to higher states, and then when they fall down, they give off light. So the fact that we're observing light being given off by this is an indication that this is an exothermic reaction. So now let's start to work through this and sort of dissect what's going on. So let's take a look at the oxidation states of the various compounds. So what we have here, so I have the answers here, but let's talk about how I got those answers for oxidation states. Now, this is an interesting reaction because in this case, the reactants are both elements in their standard states. So you can see that iron is iron solid and oxygen is oxygen gas. So when something is in its elemental form, meaning that it's not bound to anything else and it's in its elemental form, it must have an oxidation state of 0. So one of the things you're going to want to review before you really start to watch this and do this experiment is how to assign oxidation states in your textbook, in your notes from class. So you're going to want to review those notes about assigning oxidation states because the rules for that are going to apply exactly as you would in lecture. Now, so I'm going to kind of cover the rules that are specific to this. So as we said, these are elements in their standard state, so they get an oxidation number of 0. Now, when we have a compound like iron oxide, we have to start to work things out. So one of the things that we know is that oxide, which is this O in this species, oxide tends to have a -2 charge. So we can assign that just knowing that oxygen, when it forms an ion, has a -2 charge. And then from these stoichiometric coefficients of 2 and 3, we can figure out by doing the crisscross method that the oxygen, if we have 3 of those, we can take 3 times -2, and then we can say, well, this whole species has to have a 0 charge because it is not an ionic compound. This is a solid material. It does not have a charge. So we assign the overall charge of 0, and then we can start to work it out. So if we have 3 oxygens and they have a -2 charge, and we have 2 of something that has an unknown charge, so we put the charge of the iron as X, we can then solve this. So we do 3 times -2 gives us -6, which we bring over here, and that's a +6. We divide that by 2, and then that gives us an X equal to +3. So we know that the iron has a +3 charge and that the oxygen has a -2 charge. And the oxygen we know because we have to memorize the relative charges for the nonmetals. So now for half reactions, what we can do is we can start to write out what are the reactants in the product. So we know that iron solid is our reactant and our product is iron 3+. Now how can I break this apart? Well, I can break this apart because we know that the iron that's inside of this is iron 3+. We figured out its oxidation state. So to figure out how many electrons are transferred, we can take the iron as it is on the left, and we can take the iron as it is on the right, and look to see what the charges are. Now, in order to figure out the number of electrons that are taking place in the transfer, what we have to do is we have to look at the charges and make sure they balance. So on the left side we have 0 charge, on the right side we have 3 positive charges. So to get that to balance, we have to add 3 electrons to the right hand side in order to make sure that this has an overall charge of 0 and this has an overall charge of 0. So basically the charge on the left and the charge on the right have to be the same. So we can see that the iron was oxidized. Its oxidation state went from 0 to +3, and that releases 3 electrons as a product. And for the oxygen, we have O2 gas on the left and we have O2 minus on the right. So if we have an overall charge of 2 minus on the right hand side, we have to make the left hand side a -2 also. And I do that by adding 2 electrons. So now the left has a -2 charge, the right has a -2 charge, and we can see that the oxygen was reduced. So iron is oxidized, and therefore it is the reducing agent. It has caused the oxygen to be reduced, and oxygen is reduced, and therefore it is the oxidizing agent. So that covers how you can go about determining the oxidation states, whether something is oxidized or reduced, and whether something is the oxidizing agent or the reducing agent. Now, in this experiment, what we're going to do is we're going to have to be very detailed in our observations. So we're going to go into basically the lab now, into a virtual lab space. We're going to set these reactions up for you, and you're going to watch them just as you would if you were at the lab bench. So what are the things you're going to want to observe? What are the colors of the reactants? What are the colors of the products? Was any material precipitated? Did a gas form? What was the color of the gas? Was the reaction exothermic or endothermic? I'm going to help you out there since you can't physically touch it. But you will be able to see if something was endothermic or exothermic. Now, because these things because we're going to be working with a lot of different materials, we have to know, in order to understand what happened in a reaction, we have to know what the product is and what the reactants are. And the way that we can do that is we can look up what are the properties, the colors and the physical properties, meaning is it a solid, a liquid, or a gas, and what color is that solid, liquid, or gas. And then we can use this table of all of the possible compounds that are generated to sort of work out what was produced. So let's say, for example, we have a reaction of potassium permanganate, and this is a purple color, and we add something to it, and we want to know what the product was. Well, if this thing turns dark blue, meaning we go from purple to a dark blue, then we know that we've formed MnO4 3-. Or if we make a dark green, we formed MnO4 2-. So we're going to use these physical properties to tell us what the reactants in the products were. Now, an incredibly important thing to do is to make sure that you balance every reaction and use proper phase labels. So I'm going to kind of give this warning now, and then it's going to be your job to make sure that if you have to write a reaction that is balanced and has proper phase labels. You will lose points if it's not balanced and it doesn't have proper phase labels. So now the first thing we're going to do is we're going to look at a redox reaction of copper reacting with sulfur. And actually, this reaction would be something that you would do, that we would actually do as a demonstration anyway. It would look exactly like what's going on in this video, except we would do it for you, and you would watch us do it. So now let's take a look. So we're going to add, we're going to have some copper. The copper is this little string of metal that's suspended here. And the sulfur is this yellow powder down at the bottom. So now we know what the reactants look like. So now let's take a look at what happens in this reaction and start to make our observations. So what we're going to do is we're going to start to heat the sulfur, which is going to make it go into a gaseous form. And that gaseous form of sulfur is going to react with our copper metal. And that's what you're observing. What happens to the copper metal as the reaction proceeds? So just so that you know, this yellow gas that's being formed, this sort of brownish gas, that is the sulfur being vaporized from sulfur solid to sulfur gas. So I just want to point that out because it's important for you to know that's what's happening. So this reaction that's taking place is between the copper and the sulfur, the gaseous sulfur that's being generated from the heating. Okay, now let's skip a little bit ahead, and we're going to take a look at what comes out. So if you look, these are the observations you're going to start to make. So the questions that are related to this video and the observations you have to make: does the substance that came out, so this is the substance now, and you saw the substance what it looked like originally, does this resemble copper? The answer is yes or no. And then you also are going to want to put, what does copper look like? So what was your observations of copper? And what are your observations of the product after it comes out? So what does this material look like relative to what it started with? That's what you're going to write in line 1. Now, let's look at, is it possible to bend the substance without breaking it? So they're going to start to do that now. So you're going to write your observation: is it possible to send is it possible to bend the substance without breaking it? You're going to write your observations now. You're also going to write, what color is it? So hopefully you can see the color now. And then from this, you have to tell us, has a reaction occurred? So the answer is either yes or no, and how do you know? Now remember that the copper originally looked like this before the reaction started. And I can tell you that if you were to bend this, you could bend it very easily. It's kind of like bending a metal wire. When you bend a metal wire, it will bend very easily. Okay, so you can pause the video now and answer those questions before we move on to the next. Now, there's another set of questions that that we have to cover, and that is, how can we tell if the substance is copper 1 sulfide or copper 2 sulfide? Now, just before we start, remember, copper 1 sulfide means that the copper has a +1 charge. It doesn't mean that there's one copper. It means that the copper has a +1. So this is Cu+. So the stoichiometry there, because S is S2- is going to give us Cu2S. So even though there are 2 coppers here, that is still copper 1 sulfide. And then we have copper 2 sulfide. So the question is which one of these did we make? So how can we tell if it's copper 2 sulfide or copper 1 sulfide? So we can use ammonia as an indicator. So pure ammonia has a clear color. There's nothing in ammonia, and it looks like water. And when you add copper 1 sulfide, to it, it produces a deep blue solution. When you add copper 2 sulfide, it has no reaction, so you would see nothing. So when you add the product to ammonia, you get this solution over on the right. So that should tell you which one of these two was produced. So now pause this video for a second and answer these following questions. Does your product react with ammonia? Yes or no? Based on what I showed you here. Suggest a possible formula for the product. So which one of these two formulas is it? And then in line 7, you have to write a balanced reaction showing your proposed product. So you're going to write down the complete reaction with your product and then make sure that it's balanced. So you can pause the video and do that now before we move on. The next set of reactions we're going to look at are the reactions of metals with acids. And this is going to depend a little bit on, so we're going to actually be looking at the reactivity, meaning how reactive, relatively speaking, are the metals, and how reactive are the acids, relatively speaking. So reactivity is a measurement of how susceptible they are to undergoing chemical reactions in terms of when you add a metal to an acid. So if a metal is active, it will undergo a chemical reaction. If a metal is inactive in a given acid, then it will not undergo a chemical reaction. So that's what we mean by reactivities of metals with acids. Now, acids, in terms of safety, are extremely corrosive. So, and they can burn your skin if you get it on you. So we want to make sure that we wear safety glasses to prevent the acids from getting into our eyes. If the acid spills, we want to make sure that we clean up that spill immediately, so that way, for example, somebody doesn't lean their arm on it and they get burned because they don't know that they're leaning in acid. They think it's water, for example. And another thing is that if you ever get acid on your skin, you want to make sure you wash it with water to remove the acid before it has a chance to burn you. So you want to rinse your skin immediately with water to dilute the acid and get it off your skin. So the first reaction we're going to look at is the reaction of zinc and hydrochloric acid, an aqueous solution of hydrochloric acid. So according to the instructions, what you would do is you would take a small piece of zinc and add it to a test tube containing some 6 molar HCl, and we're going to note what happens. So let's take a look at that. So in this video, we're actually going to do it a little bit in reverse. We're going to have the zinc already in the test tube, and then to the test tube, we're going to add a little bit of HCl. So see, we have our HCl here in our reaction bottle, and then we're going to take a look at what happens when we add it. So now I want you to note your observations. And the gas that's formed that you could see it was bubbling. If you were to waft that gas, it would be odorless. So that is a colorless, odorless gas that is coming off of this zinc. So you've observed the reaction, you've seen that, so we can go back and just watch that a second time since it's a relatively quick video. So the minute that you put the acid in, that's what starts to happen. And that will continue to happen until the acid is totally consumed or the zinc is totally consumed. So I want you to record your observations on line 8 and then suggest some possible products for the observed reaction. So the gas that you produced is colorless and odorless. Think about what gases could be produced. Now remember, the reactants that are going into this are zinc, H+, and Cl-. So those are the only possible things that could be in the products. So that might be something you'll want to think about as you're going about looking at Table 1 to try to predict the products. Now let's look at what happens when we have copper with hydrochloric acid. So the reaction says place a 1-inch piece of copper, shiny copper, in a clean test tube and add some acid on top and see if a reaction occurs. So let's observe that. So what we have here is we have down at the bottom our copper, and we have our HCl at the top, and you're looking to see if you see any signs of a reaction. So you're going to record your observations, if there were any, and then you're going to say, is copper an active or inactive metal? So you have to decide, is a reaction taking place? So on line 11, you're going to write active or inactive, and then you're going to write whatever observations you have to support your supposition from your observations. Okay, so that takes care of zinc and hydrochloric acid. Now, let's take a look at the reactivity of copper with a stronger acid, nitric acid. So nitric acid has a chemical formula of HNO3. Now this one you're going to want to do in the hood. So and we'll see why in a second. So while holding a clean test tube in the hood, you place 1 inch of the copper and 1 ml of concentrated nitric acid. And let's look at the we'll look at the observations in just a second. So let's first observe the reaction. Okay, so what they're doing now is they're adding the nitric acid to the beaker. And this is a special type of nitric acid that's called fuming nitric acid. And then copper is added, that's just some copper wire. And you can see that, you can see what your observation should be. Okay. So that should be enough for you to have seen the total process. We'll go back and we'll watch that one more time so that you can really see it. So as soon as the copper goes in, that's what happens. And this is what you would observe in the hood. Okay, so at this point you might want to pause the video and record what you observed. You can go back and watch that a second time if you need to. Is the gas colored? So you're going to want to note what the color of the gas was that you observed. And then suggest a formula for the gas. So based on the color of the gas, you're going to want to look at Table 1 and suggest a formula. After the reaction, okay, so now for the last one we have to watch a second video. So it says, after the reaction has proceeded for 5 minutes, carefully add some water, 5 ml of water, and based on the color of the solution, what substance is present. So let's take a look at what happens when we dilute that very concentrated product. So what the person has here is some regular old water, and they're going to dilute that mixture, and we're going to see what color we get. So what you're observing is the color of the solution after we diluted it with a little bit of water. Okay? All right, so now from that, you should be able to determine what is present in the solution. Okay, so the next couple of chemical reactions that we're going to observe relate to this compound, potassium permanganate. And potassium permanganate is a very interesting compound. This compound tends to be an oxidizing agent in a variety of conditions, in both acid and base. This tends to be an oxidizing agent, meaning that the manganese, which is, if you do the math, the manganese here, if you have 4 negative charge, if you have 4 oxygens, each one of those has a -2. And then if we have a +1, that means that we have a grand total of 8 negatives and 1 positive. So the manganese has to be a +7, because 7 + 1 is a total of 8 positives, which counters the 8 negatives from the oxygen. So what tends to happen with permanganate is, because it's in such a positive or high oxidation state, it wants to take electrons to reduce its oxidation state to some lower number. And what's interesting about potassium permanganate is those compounds that have lower numbers of oxidation states will have different colors. Okay, so the permanganate ion is purple and is reduced to manganese ion, Mn2+, which has a faint pink color. So in this reaction of potassium permanganate with sodium oxalate, it tells you in the book that we should get a reaction that leads to Mn2+, which has a faint pink color. Now, it turns out in real life, it's very, very, very difficult to see that faint pink color. In lab, we tend not to see it. And actually, the video that I'm going to show you is a perfect representation of what happens when you do this reaction. It tends to lead to something that's either transparent or has a very, very slight hint of some kind of pink or brown or yellow or even orange color to it. And it kind of depends on the day and what the conditions are. So now let's take a look at what we're going to do. So we're going to take 1 ml of sodium oxalate. Now, if potassium permanganate is our oxidizing agent, that means that this is going to be reduced. And then therefore, the sodium oxalate must be what's being oxidized or is our reducing agent. So we're going to add our reducing agent, the sodium oxalate, in a clean test tube. We're going to add 10 drops of sulfuric acid. And the reason why we add the sulfuric acid is to make the solution acidic. It helps to facilitate the redox reaction from happening. Oxidizing agents can actually have different strengths depending on whether they're in an acidic, basic, or neutral condition. So in this case, we want to make sure that we're in an acidic condition because that makes the conditions right and the relative strengths correct to get us all the way down to the manganese Mn2+ ion. And then we're going to add a little bit of our oxidizing agent, 1 or 2 drops, and see what happens. So let's take a look at this. So now in this case, we have the, oops, let's go back. Okay, so they've added the sodium oxalate was in there. So let's kind of pause this video for a second because they may not actually show the addition. So what we've done is we've taken the sodium oxalate, which was in here. That's a solution of the sodium oxalate. And you can see they already added in the KMnO4. So they put the KMnO4 in, and now we have the KMnO4, and it's inside the sodium oxalate, and it's going to start to react. So let's watch that reaction take place. So now what we see is the potassium permanganate loses its color, and it goes to the solution containing the Mn2+. So the manganese has been reduced from Mn7+ to Mn2+. So you should record your observations of what the potassium permanganate looks like. So the potassium permanganate is in the background here. You can see the nice purple color. Then you add that to the sodium oxalate, and as the reaction proceeds, that purple color turns into the following color. Now, if you look carefully, you can see that that solution is not crystal clear transparent. It has a hazy color to it, and that hazy color is the Mn2+. It's not a pink color is kind of, pink is a very strong sort of word for that. I would call this like an off clear kind of coloration. So the table in that case doesn't actually lead to the perfect result. So you want to record your observations for what happened after those two were mixed. And then you want to determine, was the KMnO4 reduced to Mn2+? And what observation tells you that? Okay, so you can pause. And actually, if you notice and you look very carefully, this is kind of important for your observations. If you look at the very side here, you can start to see little teeny tiny bubbles start to form. So there is a gas that is produced from this reaction. Now, the experiment doesn't actually talk about what that gas is, but we have a species that has carbon and oxygen, and the gas that comes off is colorless and odorless. So you should be able to figure out from table 1, if we have a species that contains carbon and it generates a colorless, odorless gas, what that gas should be. And in fact, it is carbon dioxide. Okay, so now let's look at some other reactions of potassium permanganate with some other compounds. So in this case, we have potassium permanganate reacting with sodium hydrogen sulfite. So again, the potassium permanganate is going to be our oxidizing agent. The sodium hydrogen sulfite is going to be our reducing agent. So in this case, instead of doing this under acidic conditions, we're going to do this under basic conditions. And that is to get everything to be at the right strength so that we get the correct color. So here we have our solution of sodium hydrogen sulfite, and we're going to add in our potassium permanganate, and we're going to watch what happens as it reacts. And that color right there is exactly what we want to observe. So based on that color from table 1, so you're going to write down your observations. So you saw what happened when you added the potassium permanganate, what color that was. Ignore the sugar. The sugar has nothing to do with this. That's from another experiment. Okay, and then so you saw it goes from the purple color to this nice color. So you're going to record your observations, that color change. You're going to decide was the KMnO4 reduced, and then based on the color, you're going to identify the compound that's formed. Now, this is an interesting aspect to this redox reaction. So there is no video for this because it's a bit difficult to display by video. But I'm going to explain exactly what happens when we do this second part. So now, once we've generated this nice colored compound, what the book asks you to do is it says, continue to add 0.1 molar potassium permanganate, 1 drop at a time, and observe what happens until you've added a total of 10 drops. So in essence, what you're going to do is once you've made this nice color, you're going to continue to add one reactant to the other. So you're going to continue to add drop-wise potassium permanganate into this nice colored solution. Now we have to think about what we're doing. So this actually goes back to a part of chemistry where we have to think about the quantity of reagents that we're using. So this has to do with stoichiometry. So when you start out, you have this beaker that's sitting there that's full of the sodium hydrogen sulfite. So that's at this stage in the video, right here. So we have this flask that has the sodium hydrogen sulfite in it. And there's a certain number of moles of that sodium hydrogen sulfite. And then when we add our potassium permanganate in, it's going to start to react, and we're going to generate some products. And what we can see is that after adding just however many drops they added, we've gotten this green color. So presumably what's happened is we've reacted all of the KMnO4, that's gone away, and it's made whatever product it's going to make, and you can determine that based on the color from here. And the reason why we know that the KMnO4 is all gone is because KMnO4 is purple. So if KMnO4 is purple and it's present, then we would see a purple color to the solution, but we don't. So what happens is so if we continue to add potassium permanganate to this, it's going to continue to react with the sodium hydrogen sulfite until a certain point. Inevitably, eventually, we're going to get to the point where all the sodium hydrogen sulfite gets used up. So that is when we get to what we call the equivalence point, where the number of moles of one reactant equal the number of moles of another reactant, and we reach the equivalence point. So now let's think about this before we reach that equivalence point. So before we reach that equivalence point, which compound is in excess? So when we first start this, the compound that's in excess is the sodium hydrogen sulfite. We know that, so that's from this part of the reaction. We know that because the purple fully reacts and disappears and forms the green product that's there. So we don't see any excess potassium permanganate. So we know that the sodium hydrogen sulfite is in excess. So as we continue to add more and more KMnO4, eventually we're going to react all of the sodium hydrogen sulfite up. We're going to use all that up, and then the potassium permanganate is going to become the excess reagent. We're going to continue to add until we go past the amount of sodium hydrogen sulfite until the KMnO4 is in excess. And then at that point, what we're going to start to see is the solution is going to go from a green to a purple color. And the reason why it goes from a green to a purple color is because now we're going to start to see the color of the excess potassium permanganate. The green compound is still present. That's still a product. The the compound that you're going to identify is still there. It's just that the purple overwhelms it because it's a darker color. So what happens is you continue to add the potassium permanganate. Eventually, the solution goes from a green color to a purple color, and that is an indication that the potassium permanganate becomes the excess reagent. So you're gonna basically record what I told you and then explain what I just told you in terms of the limiting reagent effect. The last reaction of potassium permanganate that we're going to observe is a little bit different. In this case, we're going to be taking some potassium permanganate crystals and we're going to be adding them to hydrochloric acid. So now already, what you guys should be thinking about are what could be the potential products of this reaction. So remember that in terms of any reaction, we have to think about what are the atoms that are present in the two different reactants. So kind of just keep that in the back of your mind for when you make these observations. So it says, while holding a test tube in the fume hood. Now, whenever we ask you to do something in the fume hood, there's a pretty good bet that some kind of gas is going to get made, because that's what fume hoods are designed to dilute and to get rid of. So we're going to add 1 or 2 crystals of potassium permanganate to some hydrochloric acid, to 1 ml of hydrochloric acid. Now in the video, because you guys aren't doing this and we're doing this, we add a little bit more than just 1 or 2 crystals to really show you the product so that you can see it clearly. So normally you would just add 1 or 2 crystals and it would give a reaction. In this case, we're going to scale it up a little bit to make the reaction a little bit more obvious. So what you have in this dish is the potassium permanganate. It's a dark solid. Then in this beaker we have hydrochloric acid. And what we're going to do is we're going to take a little bit of that potassium permanganate and we're going to add the hydrochloric acid on top. Now it's a little bit difficult to see, but oops. Now, it's a little bit difficult to see, but you can see that a gas was generated, and the color of the gas is kind of evident here. Now, even if you were in lab, you would see exactly the same thing. So what you have to think about is which gas, you have to think about the identity of the gas that was created. Now, you have to think about what atoms are present in the reactants and in the 2 different types of reactants. So this gas kind of has a color to it, and you're going to want to look at table 1 along with the atoms that are in these 2 reactants to decide which gas was evolved. So you're going to want to record your observations, note the color of gas that's evolved, and then based on the color of the gas, you're going to want to identify it. So from lines 1 to 22, you now have all of the data to answer those lines. That's what we're going to be doing for experiment 4. The metathesis reactions part of this we're going to cover in experiment 5 because that focuses almost exclusively on metathesis reactions. So you should have everything you need. If you have to go back and watch the video again to see any of these reactions, that's perfectly fine. Take your time, look at the reactions, make sure you kind of familiarize yourself with all of the different observations. Be thorough, note color changes and whether a gas was formed. If a gas was formed, I will tell you what the odor is. In this particular instance, this would not be a gas that you would want to waft or smell. It's a dangerous gas, so I'm not going to. You wouldn't smell the gas. You're going to have to do it based on color. And the same thing for the brown gas that was evolved in the reaction of copper. Okay, guys, so make sure you complete your data sheet. Make sure the reactions are written, when necessary, are written and balanced and with phase labels. And then for everything else, just be thorough in your observations and make sure that you address everything that the line asks you to address. Okay, good luck, and make sure that you submit your data sheets on the day that the syllabus says to upload experiment 4.